Hello, this is Josh Cortez. This is the video submission for CSC313 final project, and let's get right into it. So I'm just going to let it run and then I'll explain what it is. Yeah, I mean, this is pretty much it. This is just our 3D rendering project. So here we have two different cartridges, the big one and the small one. And we also have the table, the texture table, and we had to handle the bouncing, or we had to do everything, but the the bouncing and the physics of the bullets, as well as the rendering of them and the sound of them bouncing as well. So let's go ahead and get right into the code. And right here, this is our or mine. Sorry, I will be only reviewing my code. So that main is our entry point. So when Java runs a program, it starts right there, and all it does is just create that one instance of the bullet hell class and calls a run on it. And at our excuse me, init and loop, it just calls init to set everything up, and then hands control the loop, which keeps the simulation running until you close the window. On the GLFW, that's a library that creates our OS window and handles the input. If it fails to initialize, we have that throw to let us know that it failed. And on here we have the GL depth test. So without it, the bullets would just sometimes not show up. So instead we have this so that the bullets behind the terrain would still appear on top, and depth testing just makes sure the closer geometry always wins. And where are we at? Right here. And then here we have the projection matrix. So this is where we set up our perspective projection, and this is what gives us the scene of, or the scene gives it a sense of depth, and we match the window's aspect ratio. And here, this is where we are reading the fractal terrain object file, as well as using the terrain PNG to make that table almost looking thing. And on the bullet system here, we have we pass in the terrain's bounding box so the bullets know where they're supposed to spawn and move, and as well as the terrain itself for height lookups and bounce physics. And on this void loop, oh, I'm sorry, I don't need to say void, but the loop that we have here, before we even get into it, we do grab the current time in nanoseconds. This is just our timestamp anchor, so that every frame we have something to compare to see how much time has actually passed. And for DT, this is how many seconds elapsed since the last frame. Dividing nanoseconds by billions is what converts to seconds. So every physics calculation in this project multiplies by dt, which is what makes it frame independent, or frame rate independent. So whenever you're running either 30 or a way higher FPS, the bullets will always behave the same way. And on that GL translate, we have our position for our camera. It just centers it. And here on the bullet system, for that kill underscore y, if the bullet somehow falls below the below y -10, we would count it as lost and we will remove it. And then for small scale and large scale, these are just the uniform scale values applied to each bullet when rendering. Large bullets are about 4 times as big as the small ones, but I mean, I don't really need to get into that. And here are just our constants of how we're going to be controlling the reactions almost of the bullets when they bounce, when they fall, and how much energy they contain when they're moving. And after updating velocity, we integrate it into position. So velocity times delta gives us how far to move this frame. 3 lines for each axis, or 3 lines, 1 for each axis. And at the clamp, we clamp the bullets X and Z to stay within the terrain boundaries. Without this, a bullet can just drift off past the edge, and we would pretty much give us a lost bullet. And on down here on that kill Y, that is where we remove the call. So if the bullet does drop below the kill threshold, it's removed from the list and is automatically just discarded. And here, this is where we're rendering the bullet. So for every bullet we push this matrix stack, we apply that bullet's position and rotation and renders it into its mesh and then pop back. So this isolates each bullet's transforms so they don't interfere with each other. And on that rotation, so when a bullet is in flight, we orientate to face the direction it's moving, and then we derive a yaw angle from horizontal velocity and pitch from vertical velocity, then apply these as rotations. So the bullet model actually points nose first to wherever it's headed. And once a bullet comes to rest, we flip it to 180 degrees on the x-axis. That's where you can see the GL rotate 180, 100, and this shows it landing upside down. A simple visual cue that the bullet has stopped and is sitting on the terrain. Large scale bullets get scaled up to 5.2 and also rotated 90 degrees on the X. That X rotation is because the large bullet OBJ is modeled along a different axis. This just correctly aligns it with the same orientation logic as the smaller bullet. And the small bullets get their scale applied, so no X rotation needed since their model is already oriented correctly. And here, this is our OBJ file parser, so it reads the file line by line and branches on the prefix. Lines starting with VN are normals, and V are vertex, VT, and UV. VTR UV texture coordinates, and F are face definitions that tie them all together. OBJ face lines look like the 1/2/3 and the 4/5/6, so on. Each group is a vertex index, a UV index, and a normal index. So we parse all three for each of the three corners of the triangle and pack them into a 9-element int array. If the file object, if the OBJ file has no texture coordinates or no normals, which can happen with the simple meshes, we add a single fallback entry so the render loop never tries to index into an empty list. And the render method iterates every face and submits its 3 vertices to the GPU as triangles. So for each vertex, it sends the normal first, so lighting calculates correctly, then the UV, so the texture maps correctly, then the position itself. And here we get to the terrain. So on that terrain underscore flatten scale, the raw fractal data can be pretty extreme in height, so the scale factor squashes down to 35% of its original height, which gives us that landscape that looks natural without random massive spikes that are mountain spikes that the bullets would disappear into. And on that float, this is just a flat 1D array representing a 2D grid of height values sampled from the terrain vertices. Instead of querying a full mesh geometry every frame for every bullet, we pre-bake this into this grid for fast lookups. And the terrain constructor does 3 things in sequence. It loads the OBJ mesh, calls parse bounds to find the terrain spatial extents, loads the texture, and then calls build height grid to generate both the height and the normal grid lookup grids. And the grid W, that is just the grid dimensions, 1 grid cell per unit, which means the grid and the terrain have a 1-to-1 spatial mapping. This makes lookups pretty straightforward. And for that float, we walk through every vertex in the or in that for loop. We walk through every vertex in the terrain mesh, which computes which grid cell it belongs to by subtracting min x and min z, and stores its y value. That's all a grid height height grid is a table of at this XZ position, and the ground is at this height. So for normals, we do a extra pass over multiple faces, so multiple triangles can share the same grid cell. We accumulate all their normals and count how many we've seen. Averaging them gives us a smooth surface normal per cell that we use for the bounce reflection math. And in that bilinear interpolation, let's see here, where's my mouse? I lost my mouse. Here you go. Right here, we have the oh, I lost it. Where is it at? So rather than just snapping to the nearest grid cell at the get height at does bilinear interpolation across the four surrounding cells, which gives that smooth height values between grid points, so bullets don't stutter when they cross a cell boundary. Yeah, let me just show you all of that code right there. And for the get center X and the get max dimension, these two utility getters feed directly into the camera positioning in the main loop. The get center X centers the view horizontally, and the get max dimension gives us a single number we can scale to push the camera back far enough to see the whole terrain. And for the terrain boundary getters, we just have those for the terrain's bounding box, the bullet system. That's what the bullet system uses to clamp bullet positions and pick random spot locations, but it never goes outside of those bounds. And the parse bounds, and yep, that's not it. So parse bounds does a second read of the OBJ file just to track the minimum and maximum X and the Z values across all the vertices. So we need these before building the height grid, so we know how big to make it. And yep, that's pretty much it for this video. Thank you.